time to look at linear regression. In particular, I want to look at the math behind linear regression. You don't need to be an expert at the math or anything like that. I just want to give you an idea of how machine learning models actually work, okay, to help you try to understand how neural networks work. Our emphasis in this class is on the code, but we do take a little bit of time sometimes to look at some theory for those of you who are interested. Okay, so linear regression. Given a set of data points, linear regression gives a straight line that minimizes the square of the distance between the points in the line. Traditionally, the least squares regression line was found using calculus. Times change. Let's look at a linear regression example. So here's a median house value looking at the average number of rooms in the target. This is in 2 dimensions. You can see that the blue line is the best fit. You can only do so good with this. And the shaded part is actually the level of uncertainty at a 95% confidence interval. So the idea is that, whether I think this might be Seaborn, if they're 95% confidence that the line is somewhere within the shaded part, but they're not sure exactly where. And so this is, you can make a prediction like if the average number of rooms were 8, then the prediction would be you go up and exactly where it would hit the line. Okay. So linear regression is machine learning. Machine learning requires data and a column to make predictions. Linear regression predicts one column, the y value, from another column, the x value. That's in 2 dimensions. Machine learning extends linear regression from 2 dimensions to an arbitrary number of dimensions. It's called machine learning because the model learns from new data. More data results in more accurate models and a better regression line. Okay, so let's look at linear regression first in 2 dimensions. The equation is y equals mx plus b. I put the times x to emphasize that in Python and coding, you need that times. You can't just write mx. In math, x is the input, m is the slope, b is the y-intercept, and y is the output. Note that x may take on any value like data points in a column. The key to finding the line of least squares is to find the right m, the slope, and b, the y-intercept. So if you have an input of x and you have weights m and b and an output of y, you may find that m equals 2 and b equals 3, and then your regression line is actually y equals 2x plus 3. Okay? Just like in algebra class. So how do we do this in n dimensions? Well, let's start with y equals mx plus b, and then flip it around, right? Totally do that. And just change the label as b sub 0, b sub 1, x sub 1. You'll see why. Those are all 2-dimensional. But now you can go on and keep going. B sub 2, x sub 2. And that's a 3-dimensional one. And you can keep going. You add another bx. And now you are in 4 dimensions. And you can keep going. And this is considered to be n-dimensional. Now, you can make a modification. If x naught is 1, then that's true, right? Because b naught times 1 is b naught. And then you have the summation of all the b's and the x's. And sometimes that's just written as y equals bx. And note that those are all n-dimensional representations. So y equals bx. In machine learning, x is the input, which are the columns, right? And b are the weights, the slope. So b is what you use to multiply the columns by. X may take on any number of dimensions. If x is 100 columns, then x contains 100 dimensions. Now b provides a unique weight for each column. If there are 100 columns, then b is a list of 100 different values. For the final result, each value in a column x is multiplied by the weight b and summed. Let's look at it with data. So here's this little subset of the California housing data. And there's, say, x1, the first column. There's x2, second column. There's x3, third column. x4, and what is that last one? That's y. That's what we're trying to predict, right? So you want to multiply that first column all by 1 weight, okay? So basically the idea is, like, let's say it's the number 2, then you're doubling like each of those numbers. And then you have the population, right? And that has its own weight. Maybe it's like -1/2. So then you add -1/2 times the next column. and so on. B3 has its own weight. B4 has its own weight. And it looks like we're done, except don't forget, you've got that B0, right? Which is kind of like your normal B, y equals mx plus b. So you can move it up or down a little bit. And it's not as significant actually as the B1, 2, 3, and 4. Key is to find the right B's. Those are the weights. That's what machine learning does, is it finds linear regression, that's what it does. It finds those values and adds them together. So how are the weights chosen? Well, you have y equals bx. The weights, also known as the coefficients, or the average range of values of b, or the range of values of b. At first try, b is completely random. After comparing the random predictions to the results, b is adjusted on whether it's too high or too low using gradient descent calculus. So it kind of goes back, okay, it's called back propagation. It goes back and it checks, how well did this one do? Okay, and it makes adjustments accordingly. You make it sound simple, right? Deep math there. During each subsequent iteration, b is adjusted until the error is minimized, right? So minimal error means maximal output. After the error has been minimized for b, the final model is selected. So how does it work with code? We already did this. I'll just give you a quick refresher. Import linear regression from sklearn.linear model needs to be changed. Model equals linear regression to initialize. Model.fit in x and y. We've looked at model.score in x and y. You can also do model.predict on a new x, which of course is very important. And we're going to look at new scoring metrics as well. All right, let's expand upon what we've learned with code.